Did you know that as of 2023, the Robinhood platform executes over 2 million trades per day, managing over hundreds of billions in assets? The secret is that building a platform to handle that volume while ensuring accuracy, security, and regulatory compliance is incredibly complex. Here's what most engineers get wrong. They underestimate the challenges of building a reliable and scalable trading platform. By the end of this video, you'll learn how to design a system like Robinhood from the ground up, and we'll see why handling that $400 billion matters so much when we discuss sharding. Keep this in mind for the scaling section. Few people know the real complexity of building a financial platform. Let's define the scope of our stock trading platform. Functionally, we need to support buying and selling stocks, displaying real-time market data, managing account balances, processing payments, and sending notifications. Non-functional requirements include high availability, low latency, target P99 less than 50 meters, strong security, and regulatory compliance with KYC, Know Your Customer, and AML, anti-money laundering regulations. We also need to support data persistence and API integration with third-party services for market data and news feeds. Robust security measures are needed to protect user data and funds. Clarifying questions. Are we supporting options trading? Margin accounts? International markets? For simplicity, we'll focus on basic stock trading in the US market, no margin accounts, and no options. We need to support market orders and limit orders. We'll also need to support fractional shares. Let's estimate the scale of our system. Assume 10 million daily active users, with 1% placing a trade per minute during peak hours. That's 10,000 trades per minute, or roughly 160 FM trades per second, TPS. Each trade generates about 1 KB of data. That's 167 KBS. For storage, assuming each user makes 10 trades per day, and we store trade history for 5 years, that's 10 M users times about 10 trades each day times 1 KB trade times 365 days times 5 years equals roughly 182 TB of storage. We also need to consider market data updates. If we are tracking fights and stocks and each update is 100 bytes and updates happen 10 times a second, that's 5 MB/s of market data. This is where most people go wrong. They forget to account for market data volume and the impact on network bandwidth. We also need to estimate the number of accounts, which will impact our database sizing. We also need to consider the peak QPS during market open and close. Now that we have the estimations, let's look at the high-level design. We'll separate the read and write paths for optimization. The write path handles trade orders, while the read path serves real-time market data and account information. The client sends requests to a load balancer, which distributes traffic to the API gateway. The API gateway handles authentication, rate limiting, and routing. A concrete API endpoint would be post, API CS v1 orders, stock is symbol, quantity, order, key, type, which returns flash order ID, status, created at build. From there, requests are routed to the appropriate application servers. We use Kafka for asynchronous processing of trades and market data updates. Why Kafka? Because its append-only log provides replay capability and guarantees ordering, which is critical for financial transactions. RabbitMQ was considered, but it would lose events once acknowledged, which is unacceptable for financial transactions. The write path updates the primary database, and changes are asynchronously replicated to read replicas. Here's the twist. We'll use a CDN like Cloudflare to cache static assets and reduce latency for users around the world. This separation allows us to scale each path independently based on its specific needs. We'll use gRPC for internal communication because it's more efficient than REST. We'll also use a message queue for order placement. Let's dive deeper into the core logic, the order management system. When a user places an order, it's first validated for sufficient funds and compliance checks. Then, the order is sent to the trade execution engine. We need to ensure that order processing is idempotent. Why? Because network failures can cause duplicate order submissions. To achieve idempotency, we assign a unique ID to each order and store it in the database. Before processing an order, we check if the ID already exists. If it does, we return the previous result. The trade execution engine matches buy and sell orders based on price and time priority. For order matching, we use a priority queue data structure. The interviewer might ask, why not just use a simple array? The reason is that a priority queue provides O log n time complexity for insertion and retrieval which is much more efficient than ON for an array, especially under high load. We could use a heap-based priority queue, implemented using the heap queue library in Python. Now at this point, your interviewer will push back, what happens when the matching engine fails? The answer is that we need to have a backup matching engine ready to take over. We also need to ensure that all in-flight orders are persisted to a durable queue so they can be reprocessed by the backup engine. This is a common mistake, forgetting to handle failure scenarios. Most candidates stop here. Strong answers also address partial fills and order types. Stop. Think about this. What happens if the backup engine also fails? We need to implement circuit breakers to prevent cascading failures. We can use the Hystrix library for circuit breaker implementation. Let's look at the data model. We'll use PostgreSQL for our primary database. Why PostgreSQL? Because it offers strong ACID properties, which are critical for financial transactions and ensuring data consistency. We considered MongoDB, but its eventual consistency model is not suitable for financial data where immediate accuracy is paramount. Here's a schema for the trades table. Trade.ID, UID, primary key, user's ID, UID, foreign key, stock key symbol set, varchar, order type, boy, enum, market, limit, quantity, integer, price, decimal, timestamp, status, enum, pending, filled, canceled, created at, timestamp, job ID, or UID, parent ID, your UID. Pause and think. What's missing from this schema? Audit fields and lineage tracking are critical, but so are indexes for common queries. We'll add an index on user ID and stock symbol to speed up common queries. We also need to store the exchange the trade was executed on. We also need to store the commission charged for the trade. Now let's talk scaling. To handle the read load, we'll use a cache aside pattern with Redis. On a cache miss, we query the read replicas and backfill the cache. This keeps our P99 latency under 50 milliseconds for read-heavy workloads. We use database replication to distribute the read load across multiple read replicas. For the write path, we'll use database sharding. We can shard by user ID to distribute the write load across multiple shards. We use consistent hashing to ensure even distribution of data across shards. Why consistent hashing? Because it minimizes data movement when shards are added or removed. Standard modulo hashing would require remapping all keys, leading to cache invalidation storms. Remember that $400 billion in assets we mentioned in the hook? This is where it matters. To handle that volume, we need a robust and scalable architecture. For static assets like images and CSM, we'll use a CDN like Cloudflare. This reduces latency and improves user experience. Your interviewer will push back here. Why not just use a single large database? The answer is that a single database will eventually become a bottleneck. Sharding allows us to scale horizontally and handle the increasing write load. Here's the twist. We'll also use rate limiting to prevent abuse and ensure fair usage of the platform. We'll use a token bucket algorithm for rate limiting. We can also use Bloom filters to prevent cache pollution. Sharding is also important for regulatory compliance as it allows us to isolate data based on jurisdiction. For reliability, we need to consider fault tolerance, monitoring, and alerting. We'll use multiple availability zones to protect against regional outages. We'll implement health checks for all critical components. If a component fails, we'll automatically fail over to a backup. We'll use Prometheus and Grafana for monitoring. We'll set up alerts for critical metrics like CPU utilization, memory usage, and error rates. We'll also use distributed tracing to track requests across multiple services. This helps us identify bottlenecks and performance issues. An experienced interviewer will probe what happens when the primary database fails. Your answer should be that we'll automatically fail over to a standby replica. We also need to ensure that all in-flight transactions are rolled back or replayed, and that the failover process itself is monitored. Few people know that you can also use chaos engineering to proactively test the reliability of your system. We'll use Jaeger for distributed tracing. We can also use Kubernetes for orchestration. In summary, we've designed a scalable and reliable stock trading platform. The key trade-offs include consistency versus availability and cost versus performance. The biggest potential bottleneck is the database, so it's crucial to optimize database performance. Next steps include implementing real-time market data streaming, using WebSockets, adding support for options trading, and improving the user interface. Remember, system design is about making informed trade-offs and building a system that meets the specific needs of the business. The payment gateway, ledger, transaction service, fraud detection, and API gateway are all critical components.